Thank you. Thank you. So this is the second part of my talk. And so this is still joint work with Professor So, work in progress. Yeah. So for those who were here last Wednesday, I'm going to give a brief revision of what I said, and for those who weren't here, a brief summary. Okay. So the object I want to investigate is the quadric QM, which is a complex hypersurface of complex projective space of dimension m+1, which is given by the homogeneous quadratic equation where the sum of the squares of all the coefficients of a vector is equal to 0. Yeah, so these are homogeneous coordinates, and this symbol denotes the complex line spanned by the vector z, and we have a natural projection here from the 2m plus 3 dimensional sphere. This is the Hopf map, okay, or Hopf vibration, which is a circle vibration which is sitting inside Cm plus 2. And here we have an inverse image, which I denoted by Q twiddle M, and we identified that this is the space of orthonormal two frames in C in Rm plus 2. Okay, so this is inside here. And then, so I explained a bit the geometry of the complex quadric using what is known about the geometry of complex projective space, and in particular what we identified is that there is a S1 bundle, which I denoted by A, S1 bundle of complex conjugations on the quadric, which we obtained by, this is a complex hypersurface in here. For each unit normal vector we have a shape operator. The shape operator we saw is we can describe using just complex coordinates. Shape operator is just given by a complex conjugation, and by rotating the unit normal we get this S1 bundle of complex conjugations. And then once we had this S1 bundle of complex conjugations, I was able to get an explicit description of the curvature tensor, which I don't want to write down anymore, but it's something depends on G, the metric on the quadric, the complex structure on the quadric, and an arbitrary complex conjugation in here. Yeah, and then in the end I described what singular tangent vectors are on the quadric, and there are two types of singular tangent vectors. A principal ones, which are just fixed by a complex conjugation, and isotropic ones, which are isotropic with respect to any complex conjugation. So that's mainly the revision or summary of the last lecture. And now I want to start to talk about real hypersurfaces. So the idea of, what we're trying to do is give geometric characterizations of certain hypersurfaces in spaces. So, for example, this is well known here, in complex projective space, CPM, we have certain model spaces and hypersurfaces. Yeah, we have these, perhaps that's best known here, the type A, B, C, D, E, and these are just the homogeneous hypersurfaces. Yeah? Homogeneous hypersurfaces. In the complex two-plane Grassmannian, we encountered this here on previous days. We have two types, again type A and B, that's all. And again, these are just the homogeneous hypersurfaces. And I want to explain next what we have here for the quadric, because that's useful to know. Yeah? What are the homogeneous hypersurfaces in the quadric? And what we will see is actually, or what is known, there are probably four types, A, B, C, D. I don't know which one is which. It's probably one has to find it out by investigating this further. But there are four types of homogeneous hypersurfaces. And I want to describe these. So when we have... So what is a homogeneous hypersurface? A homogeneous hypersurface is the same as a generic orbit or principal orbit, generic orbit of a cohomogeneity one action, cohomogeneity one action. Yeah, that's it. Cohomogeneity one action is an orbit, is an action for which the codimension of a generic orbit is 1, so it's a homogeneous hypersurface. So classifying homogeneous hypersurfaces is equivalent to classifying cohomogeneity one actions, and on irreducible simply connected symmetric spaces of compact type, this was done by Kohlroas. Yeah, Kohlroas classified such actions, so one just needs to look at his classification to find out, well, there are just 4 such actions. So classified, so these actions were classified by Kohlroas on, what shall I say, simply connected compact and maybe irreducible symmetric spaces. Well, it's a nice list which he produced, and so we can read off from his paper that there are 4 such actions on the complex quadric. So on the quadric there are 4 homogeneity one actions. Because when I say 4, I mean up to conjugacy, because one can always conjugate groups and things. And so they are given by, first, we have, just to remind you, we also have a homogeneous space description on the quadric. Just to remind you. So the quadric as a homogeneous space or as a symmetric space is SOM plus 2 over SOM times SO2. I described this in the last lecture. So inside SOM plus 2, we have naturally SOM plus 1, by just forgetting the last coordinate. Yeah? So we have a natural embedding. So this is one. The second one is one in SO. Wait. So I should now write 2k plus 2. So M has to be an even number. And inside there we have the unitary group, UK plus 1 in SO2k plus 2. Going to explain how this sits inside there later. Yeah. Then we've got an action. So this is an action on a quadric of even complex dimension. Yeah, so that's on Q2k. So this is on QM. So then we have inside SO4n plus 4, we have as a subgroup SPn times SP1. This is SPn plus 1, sorry. So this acts on a complex quadric of dimension 2n plus 2. No, it must be, what is it? 4n. Just have to forget 2 dimensions, so that's 4n plus 2. Yeah, so dimensions are quadrics on dimension 4n plus 2, and then there is an exceptional one. It's spin 9 sitting inside SO16, and this acts on the 14-dimensional quadric. So there are 3 series of homogeneous hypersurfaces and 1 exceptional homogeneous hypersurface. Okay. So I want to explain these a bit more. How do these? I want to explain a bit the geometry of these hypersurfaces. So what we understand well are the first 2. What I don't understand well at the moment is this one. What I understand reasonably well is this one. So I start with the simple one, the first one. So what we do is we consider embedding from the m-1 dimensional quadric into the m-dimensional quadric, where we map Z0, oh no, what do I need? Z1 up to Zm plus 1, map this to Z1 to Zm plus 1, and then we put a 0 into the last component. So this is it's not difficult to prove. It's a totally geodesic embedding of the m-dimensional quadric, m-1 dimensional quadric, into the m-dimensional quadric as a complex hypersurface. It's a standard embedding. We just forget the last coordinate. So then what one can show is that for all points Z in the m-1 dimensional quadric, and for all conjugations A in A at the point Z. Yeah, we have this circle of complex conjugations. So I pick an arbitrary one. The tangent space of the quadric is invariant, and of course then, because that's a symmetric or self-adjoint endomorphism, the normal space is invariant. Why is this? Because if you remember the complex conjugation, complex conjugation is just ordinary complex conjugation on a complex vector space. So the tangent space in the quadric, what you do there is you just forget the last coordinate. So this will leave invariant everything. Yeah, so it leaves tangent space and normal space invariant. So in particular, So the normal space has real codimension 2. It's a complex line. Has real codimension 2. This tells us that, and we have this circle of complex conjugations. So for every normal vector, for every unit normal vector, there must be a conjugation which fixes this normal vector. Yeah, so every normal vector must be an A principal vector. It's fixed by some conjugation. And that's an important observation, because this tells us that every normal vector of the quadric is a singular tangent vector of the quadric in which it is living. Yeah, so the normal bundle consists of singular tangent vectors. So since the dimension of the normal space of the quadric is equal to 2, we have that for every normal vector of the quadric there exists, or let's say of length 1, we are only interested in unit normal vectors, there exists a complex conjugation which fixes the normal vector. So thus, the normal bundle of the quadric consists of A principal. So these are the singular tangent vectors. It also tells us that we can split the tangent space of the quadric nicely into the +1 eigenspace and the -1 eigenspace of this conjugation. Yeah, so what we get is it's the +1 eigenspace, but of course I need to remove the normal vector plus j of this, which gives us the -1 eigenspace. Okay. So this tells us how the quadric, a bit about the geometry of the quadric. So now SOM+1, the group I want to consider that acts on this is it's the group of all isometries in SOM+2 which fix the m-1 dimensional quadric. In fact, I want to take the identity component of this because we may have different components. So this is the SOM+1. It's just the group where we forget the last coordinate. Yeah, so then this group SOM plus 1 acts on QM with cohomogeneity 1, and QM minus 1 is a singular orbit of this action. So this tells us that the generic orbit is a tube around this quadric. Okay. Now we have a homogeneity 1 action on a simply connected compact space. This must have two singular orbits. One we identified. This is actually how we constructed the action. This is the quadric, and one can work out the second singular orbit. I don't want to do this, and now just give this to you as for information. The second singular orbit is an m-dimensional sphere Sm in the quadric, which is embedded in the quadric as a real form. Yeah, and we heard this 2 days ago in 2 talks by Tanaka and Sakai. Real form is a totally geodesic, totally real, half-dimensional submanifold of the space. So these generic orbits, or the homogeneous hypersurfaces, can equivalently be seen as tubes around this real form Sm. Yeah? One thing one needs also to clarify is what is the possible radio of the tubes. So for this, one needs to calculate the distance between the two focal sets. One can work this out. So the distance between the two focal sets, the m-1 dimensional quadric and the sphere Sm, with the normalization of the metric. That's the way we constructed it through all these as a submanifold from the complex projective space, is pi divided by 2 times square root of 2. Yeah? So the tubes are defined for all radii between 0 and pi over 2 times square root of 2. Hmm? So the next interesting question is really now to understand more about the geometry of the tubes, and this is, well, the first step is to calculate the shape operator of this. And there is a general method for calculating the shape operator. Maybe I should explain this, how this works. So how to work out the shape operator of a tube. So there is a general method that works in a general Riemannian manifold. So suppose we have a submanifold. I can use different colors now. Let me do this. So suppose here we've got M. So this is M bar is our Riemannian manifold. M bar, just an arbitrary Riemannian manifold. So here we have a submanifold. And then we want to determine the geometry of the tube around it, just assuming it is defined, but always locally, and for small radii this is well defined. Okay, so we work out the tube. Let's denote this tube by mr. So we assume that the distance here from here to there, somehow, no, it's not good to write from here to there. So the distance between m and mr is r, so it's a tube of radius r. And we want to determine the shape operator of the tube from the shape operator of the submanifold. What we do is, so we pick a point here, okay, and pick a normal vector, say psi, which is perpendicular to the submanifold, and then this determines, we take the geodesic, say here, gamma psi, it's the geodesic in M, given by the initial values gamma of naught is equal to, say, P, or let's say O. I always like O as base point. Let's call this point O. Now that's O. And the initial direction is our normal vector. So then here we've got the point gamma psi of r, and we are interested in working out the shape operator at this point. Yeah? So we want to know what is this. And what we need to do for this is we have to solve a second order differential equation. And it's a rather simple differential equation. Write this down here. Yeah?
Before you erase that
yeah.
at the bottom, this so the Qm minus 1 Sm
yeah.
is submanifold for the CPM, right?
Not for Qm.
Not for Qm.
Qm. They're both in Qm.
So
in the quadric.
So those distance looks like it should be, look like the independent of the M and the N, right? The ambient.
That's right.
Some ambient space.
Yes, it's the independent of the dimension.
That's very,
yeah.
Very interesting.
Yeah.
You have written actually
yeah.
that part in focal variable. So
yeah.
gamma cosine the geodesic
M bar. Yeah. Thank you. Of course, it must be a geodesic in the ambient manifold. Thank you. So, I define gamma perp. Gamma perp as a vector bundle along this geodesic, which consists of all the hyperplanes which are perpendicular to the tangent vector of the geodesic. Yes, so gamma perp of T is the orthogonal complement of the tangent vector. Yeah, so what we have here is, so suppose we have gamma of T, there we have gamma dot of T. So what we take is here is the plane which is perpendicular to the vector of the geodesic. Yeah? So what we get through this is a vector bundle along the geodesic of hyperplanes. And on this vector bundle along the geodesic, now write down a second order differential equation. Y double prime plus r gamma y equal to 0. Where r gamma of t is the Jacobi operator with respect to the tangent vector of the geodesic at the point t. Yeah, so this is an endomorphism valued second order differential equation. In order to get a unique solution, we have to impose two initial conditions. So what I do is I impose the condition y of 0 is equal to I 0, 0, 0, and y prime of 0 is equal to, here I have minus the shape operator with respect to psi, I 0, 0. So what we have is a psi is the shape operator of m with respect to psi. And the decomposition with respect to the decomposition, the tangent space, or say gamma perp of 0 is the tangent space of m at O plus the normal space of m at O minus the normal vector. Yeah, so what we decompose is, this is a hyperplane. So this hyperplane at this point decomposes into the tangent space of m at O and the remaining part of the normal space. Yeah? So this gives us a decomposition here for the initial values. And then, so let D be the solution of this equation. Then S of R equal to minus, is it D prime? Yes, it's D prime. So minus D prime of R composed with the inverse of R is the shape operator of MR with respect to, I think, with respect to this normal vector then, gamma psi dot of R. So what one needs to do is, one needs to solve the second order differential equation, work this out, work out the inverse and the derivative, compose this, one gets the shape operator. This is the general method in an arbitrary Riemannian manifold to work out the shape operator of a tube. And you see what one really needs is the curvature tensor, yeah, in order to work this out. And one needs to know the shape operator of the submanifold. Now in our case, when I don't apply this for the quadric, see, it becomes rather simple. First is, if m is qm minus 1, it's totally geodesic. Then we have a 0 here. That simplifies it considerably. Yeah, for a totally geodesic submanifold, this bit is 0. Second, the curvature tensor we knew explicitly. So one can work out this Jacobi operator. I wrote this down. So for so when we have now Qm minus 1 in Qm, when we apply all this, our Jacobi operator arc⁡ of z, so this is what we need here. We insert the normal vector here, xi, at the point O, is z plus az minus 2 times g of z xi xi plus 2 times g of jz j xi j xi. And what we see is, it's not difficult to see that we only have two eigenvalues. Zero and 2 with corresponding eigenspaces j of Va minus arc⁡ plus arc⁡ and V of A minus arc⁡ plus R j xi. Yeah, so what does this mean? 0 means, so this one, we take, let's take this one here. So we have a vector in the +1 eigenspace by A, so a vector which is fixed. So Az is equal to Z. Yeah, that's what this means. Az is equal to Z. So what we get here is Z plus Z. And then here when we are perpendicular to xi, this is 0, and then this is 0 as well. Yeah, and you can easily check that one has only these two eigenvalues. So you see this, okay. So now when you look at this, here we know this we can diagonalize, and we have only two eigenvalues, 0 and 2. And it respects the decomposition of the tangent space. Because our tangent space of the quadric, that's quite crucial here, also respects this decomposition. Yeah? So when we have this normal vector xi, we know that j xi is normal because we have a complex hypersurface. So j xi is normal. So this bit in the +2 eigenspace corresponds to this here. See here, our I is that's just a function. This is just one-dimensional. Corresponds to what is left in the normal space. This is one-dimensional. Here we have then just a 1. Here we have a 0. Here we have a 2. So we get the differential equation y double prime plus 2 times y equal to 0. And the initial value y of 0 is 0. Y prime of 0 is 1. This relates to these tangent, sine and cosine functions. This gives you the solutions, and you work this out, and you get as a solution something as a function. It's cotangent of the relevant function. Yeah. So that's what one gets, and this is how one can work it out explicitly. You see, now one can reduce this just to a set of 3 differential equations. So one for the normal space, where we have 2, and for the tangent space, we decompose this further into 2 bits, namely the 0 part and the 2 part. So altogether what we get is just 3 principal curvatures. And they are constant because it doesn't depend on the normal direction. Yeah? So working this out explicitly, what we get is principal curvatures 0, which comes from the tangential bit of 0 here, because our differential equation is y double prime equal to 0, because we have the 0 here. Initial value y of 0 is 1, y prime of 0 is 0. and we put this together, what we get is 0 as a solution. We have to work this out then. And then for the other two, what we get is square root of the tang of square root 2r. This comes from the 2 here, so the tangential bit of 2, and we have initial value 1 here and 0 here. And then finally we get minus square root of 2 cot square root of 2r. And this comes from the normal space, which I just explained. So for this one here, the eigenspace is r times j of the normal vector, or the parallel translate of this. For here, this comes from the 2 eigenspace, so it's v of a minus r psi. So this is the fixed point set of the conjugation. And for the other one, it'll be just this. This is the normal vector, which we don't consider anyway, so it's just that, what is left. Yeah, so we see we have we get the principal curvatures, we get the principal curvature spaces. We also have the multiplicities, because we just have to count dimensions. Multiplicities, dimensions, so this is m minus 1, this is m minus 1, this is 1. What we see is j of the normal vector is a principal curvature vector, so this is also a Hopf hypersurface. Okay. And also what we see is when we J interchanges these 2 eigenspaces. Yeah, so they are real. So if we work out this, this tensor condition as phi plus phi s, because it commutes these two, what we are just left with is this phi leaves this 0, so we're just left with this eigenvalue, so that's square root of 2 tang square root of 2 times r applied to phi. That's what left. So this tells us also that the tube is a contact hypersurface. So we already get some geometric information for these tubes by working out the principal curvatures, the principal curvature spaces, using the standard methodology. Yeah. So, any questions about this? So you see, we understand quite well the geometry of this particular homogeneity 1 action, or of these particular hypersurfaces. In a similar way, we understand well the geometry of the second homogeneity 1 action. So I now go to the second action, say a bit about this. So in this case, what we need is an even dimensional complex quadric. So we say m is equal to 2k. And I look now at an embedding of cpk into the even dimensional quadric. We map z1 up to zk plus 1, homogeneous coordinates on cpk. Now I want to put this into the quadric. Remember, this quadric lives inside cp2k plus 1, so we need 2k plus 2 coordinates now for the vector that I write down. Yeah? And what I do here is z1, I keep this vector. Of course, I mean, this would be fine putting in CP2K plus 1, but you see the squares of this are not equal to 0. So it's not, this image will not be in the quadric. So now I have to add something so that when we square, we get something that's equal to 0. And how do we get this? We multiply each coordinate with y, because I squared is equal to -1, and then everything goes to 0. Yeah, so it's I times z1 to I times zk plus 1. Yeah. And this is a totally geodesic complex embedding. Okay. And then what we do is we apply the same machinery, and I don't want to write down this now all in detail, just say what one gets if one does just continues to work along the same lines. So first this one gets that this CPK is an orbit of UK plus 1 times what is it? Which point did I take? Oh, I just 1, 0, 0, I, 0, 0. And this UK plus 1 sits inside the SO 2K plus 2. So this is how one gets this particular embedding as an orbit of a UK plus 1. One works out the second singular orbit. Second singular orbit is another CPK. So in fact we have two singular orbits, and both singular orbits are complex projective spaces of the same dimension, CPK. Yeah? So it's another CPK. So let me denote this by let me call it CPK twiddle. It has the same dimension. And then one can work out the distance between these two complex projective spaces in the quadric. And what one gets is oh yeah, that's equal, it's easier, just pi over 2. Yeah. And then one can work out the principal curvatures. Oh yes, so in fact is another thing what one needs to work out first, the normal bundle of CPK consists of A isotropic singular tangent vectors. And the tangent bundle as well. So again, this is these CPKs are in a quite unique, have a quite unique embedding into the quadric. Yeah. So they are tangent spaces, and tangent vectors and normal vectors are singular tangent vectors. They're isotropic vectors. And then one can work out the principal curvatures. And there are 4 of them. Tang R 0 minus cot R minus 2 times cot 2R. 4 distinct constant principal curvatures. The corresponding eigenspaces one can work out are the tangent space of the quadric, of the complex projective space, translated parallel along the normal geodesic, minus the complex line spanned by A psi. A is a conjugation, and A psi is an eigenspace with respect to the 0 eigenvector, and minus cot r comes from translating parallel the normal space. We of course have to remove the normal vector or the complex line of the normal vector, and what is left for the final one is rj psi. So again here what we have, we can work out the multiplicities. In the last one, that's 1. This is a complex line. This is 2. This is the dimension of CPK minus 2. So that's 2k minus 2. And that's the dimension of the normal space. That's 2k minus 2 minus 2k minus 2. So 2k minus 2. So what do we see? What can we see from this about the geometry of the tubes? So if we say M is a tube of radius R, around CPK. So our first observation is, again, J of the normal vector is a principal curvature vector, so we have a Hopf hypersurface. Second observation is all the other eigenspaces are invariant by the complex structure. Yeah? So all eigenspaces are invariant by the complex structure. This means that S phi is equal to phi S. S is the shape operator of the tube. Now that's the writing this down. So but it is known that this condition is equivalent to saying that the rate flow, so this is the flow on the hypersurface coming from the Hopf vector field, is isometric. Yeah, so the rate flow on M is isometric, which is a nice geometric property for the hypersurface. Okay, so this is what we can say about this this particular hypersurface. Now, for the other two, it's much more difficult. The reason is that the singular orbits, they are not totally geodesic submanifolds. In fact, it's not so clear really what the geometry of the singular orbits is. So that really needs much more work. Yeah? So this is why we can't say much more at the moment about the other two types of homogeneous hypersurfaces. Then, of course, interesting questions are, is the converse true? Can one actually characterize these hypersurfaces by these properties? Here is the, if you have a hypersurface in a quadric for which the rate flow is isometric, is it this one? Yeah, so the is actually quite, see, isometric rate flow on a CPM, the hypersurfaces with isometric rate flow are tubes around CPK. Yeah, so this is known, it's a classic, who proved this? I forgot who proved this, but it's a classic result. In the complex two-plane Grassmannian, Professor Su and I proved that this is, if you have a hypersurface for which the rate flow is isometric, it must be a tube around a G2 C m-1. Is that right?
Same plus one.
That's plus 1. But then it's right. Yeah? So the question is for the quadric. Yeah? So what there, when you look at this, really what you would intuitively, what you would like to put here, which would fit into this scheme, would be qm minus 1. Right? But this is not true. Yeah, for qm minus 1, that's disappeared now, but qm minus 1 is a contact hypersurface. It can't have isometric rib flow. So this is not true. So you see, when you just follow your intuition, you don't get the right result. Yeah, so in fact, something different happens here. It's not clear to me why this happens, but it's a different type of hypersurface where you suddenly have isometric rib flow. Yeah, it's a tube around CPK. So we know this is an example, but the question remains, is this the only one? Yeah? And I think my time is over now, and I stop here. Thank you for your attention.